All right, ready for our next list of rules to memorize? Well, on the bright side, there's only one rule for this chapter, for this particular video, and that is convert everything into secants or cosecants. But just FYI, in this video, we're only going to do powers of tangent or cotangent with nothing else. So we're not going to have any secants or cosecants thrown in there. It's just going to either be tangent to a power or cotangent to a power. And most books really emphasize tangent and not cotangent, so I'll just throw a cotangent on the end, but the process is the same. We're just going to use the Pythagorean identities to convert all these. All right, so first things first, I always want to warn you that calculus teachers and books, they throw regular u substitution problems into the middle of chapters about crazy stuff like integration by parts or these trig integrals and powers and things. So whenever you sit down to a problem, first thing you always do is just see if it's a simple integration. So for all the ones on this page, it's a simple integration. If we just make u tan x, and so this would be a power rule with u to the third, derivative of tangent is secant squared. So this is actually, even though it looks bad, it's just a du for a tangent power rule problem. Same thing here. Cosecant squared is the derivative of cotangent. There's a minus sign in there we'd have to balance out front, but the point is that if your u was cotangent x, your du would be negative cosecant squared, which means it's a power rule problem. Our u is just going to integrate to 1/2 u squared. There's u to the first, that'll integrate to 1/2 u squared. Last one, now obviously I broke this out already, but see how we have cosine cubed and a cosine and a cotangent? Cosecant cotangent is the derivative of cosecant. So again, this is our u. So it's a power rule. U to the third is going to become 1/4 u to the fourth. And of course, we'll have to, the fact that there's a 3 here means we need a 3 here, which means we need a negative, 1/3 out front. And then maybe it's negative because it's cosecants and whatnot. But the point is, always look for that u sub right off the bat. See if you can get, see if you can pick anything in the problem as a u, that the rest of the problem would then become your du. All right, so if you ever have a tangent or a cotangent to a high power, all you do is convert it to secants using the Pythagorean identity. So the Pythagorean identity, recall, is for tangent squared. So we start with sine squared plus cosine squared equals 1. And then to get the one with tangents in it, I'm just going to divide everything by cosine squared. So that's going to lead to tan squared plus 1 equals secant squared. And of course that means that tan squared would be secant squared, just put that one on the other side, minus 1. So the integral of secant squared is really just the integral of secant squared minus 1 dx. Now you might be thinking, that's not that great, but yeah, it is, because if you break this up, you can either integrate it just looking at it the way it is. If there's an x in there I didn't write down. If you break this up into two integral problems to make it more obvious and make less mistakes, you'll see there's the integral of secant squared x dx minus the integral of nothing, 1 dx. So that's simply going to be the integral of secant squared is tangent, and minus x plus c. Alright, so you can see that converting tan squared, which doesn't have a straightforward integral, to secant squared minus 1 gave us a very straightforward two-term integral. Alright, so higher powers of tangent, same story. We're going to use the Pythagorean identity once again. Now there's a subtlety here, which is, this particular problem, we're going to use Pythagorean identity once, but not twice. So the temptation would be to convert this into a, figure, hey, tangent to the fourth is really tan squared times tan squared. And each one of these would turn into a secant squared minus 1. But you don't want to do that actually in this case. You just want to convert one of these to secant squared minus 1. So we're going to do the integral of, we'll leave one as tan squared x, and the other one we'll do secant squared minus 1. Alright, so that is going to be the integral of tan squared. So I'll just sort of distribute this, separate into the two terms, minus the integral of tan squared x dx. All right, so as you can see at this point, I've got a power rule with a du that's matched. So for this first integral, if I just have u equals tan x, then my du would be secant squared x dx. Oh, surprise, that's what I've got, right? So this just integrates to, this is u squared, so that becomes u third, so 1/3 tan cubed x. And then this tan squared, I've got to do the same thing. That's just the problem we did on the previous page, right? So I've just got to convert this to minus the integral and convert that tan squared into secant squared minus 1. So I've got this minus sign right here. That goes right there. And then in parentheses, I'm going to put the integral of this. Secant squared just integrated to tangent. And then -1 just integrates to negative x. And of course I can distribute out this negative or just leave it the way it is, but I'll distribute it in. So we get 1/3 tan cubed x minus tangent x plus x plus c. Alright, so that may, and I feel like the big trick on this one was to only do the secant squared minus 1 to one of the tangent squareds, not both. But in the next video, you'll see that we'll actually be able to deal with if we a secant to the fourth, which is what we would have gotten if we had done them both at the same time. So in these problems, there's often more than one way to do the problem. To work this particular one without involving any secants, I had to only convert one of them, but in the next video, we'll see that we could have converted it, integrated it either way. All right, so odd powers are a bit uglier. They're only a little bit uglier because everything doesn't integrate perfectly. So you'll see what happens. Once again, anytime I have a power of tangent, nothing else involved, I'll want to turn all that I can into secant squareds. So I'm going to leave a tangent theta, but I'm going to turn the tan squared that's left. So if I pull out a tangent, I've still got tan squared. That's going to become secant squared. All right, so algebraically, that was pretty straightforward. So at this point, I'll break it into the two separate integrals since I have two terms here. So I've got the integral of tangent times secant squared. And then I've got minus the integral of just tangent. Oops, it's not theta, that's x. Alright, so integral of tangent secant squared, if my u is tangent, then my du is secant squared. And that's what this is. So this is simply the integral of u to the first. So that'll be 1/2 u squared. So that's 1/2 tangent squared x. Now the integral of tangent, this is the one that's a bummer. And that's because tangent's not the derivative of anything. So what we have to do is use a natural log rule. And you could, if you happen to have this integral memorized, you're welcome to do that. The way they get that integral formula, though, is they do it like this. So this will be the integral of sine x over cosine x. And you can see that if our u was cosine x, our du would be negative sine x. So negative sine x dx. So if I rewrite this in u notation, that would be the integral of du over u, which is natural log. So this becomes ln of u. And of course u was cosine x. So we end up with 1/2 tan squared x plus, because I made this a plus when that negative sign came in, plus the natural log of cosine x. Alright, so that was a little hard to follow, but the point was that tan x can be integrated by turning it into a sine over cosine, and then this is your u, and this is your du. So 1 over u integrates to natural log, and that's how we ended up with this. And of course our u was cosine x, so that's what this became. That's how we ended up with natural log of cosine x. Alright, one of those formulas you don't see too often, the integral of tangent. You can either memorize it or derive it each time, the way we just did with natural log. Alright, and just to mention that cotangent is the same as tangent, right? All the same identities apply, just slightly different versions of them. and of course it integrates straight up. So cotangent squared, that's an even power of a tangent type thing, so we're going to convert it to cosecants in this case. So just like cotangent squared, you can derive it using the Pythagorean identity again, but cotangent squared is going to equal cosecant squared x minus 1. So it's going to be integral of cosecant squared minus 1. So that's the integral of cosecant squared dx minus the integral of just 1 dx. Integral of cosecant squared is negative cotangent x, and dx is just x. Alright, so the only trick to doing cotangents is you got to remember that there's negative signs in the integral formulas for cotangent and cosecant. That's things in a nutshell. Basically, if you have powers of cotangent or tangent, you're always going to want to just convert using the Pythagorean identities. And there is no separate rule for even versus odd.